Alright everyone, let's dive into a crucial step in the machine learning pipeline, feature engineering. So what is feature engineering? Simply put, it's the process of using domain knowledge and data analysis to create new features from existing ones. Why do we do this? Well, often these engineered features can capture underlying patterns or relationships more effectively than the raw data, leading to better model performance. So they can improve model accuracy, capture complex relationships, make data more interpretable, and reduce dimensionality sometimes. Now, let's create some new features based on hypotheses about our customer behavior. All right, let's engineer some new features. So first of all, there are some original categorical features is in our data set. I used it for like exploratory data analysis previously. So we'll just drop them first because we already create dummy variables for the variables for the those original categorical features. And first, the new engineer feature that I will create is a transaction frequency. So the intuition here, how often does the customer transact relative to their tenure, which is the amount of time we have them as our customers. Well, I think it's like this is definitely makes sense because it tells us how often a customer used their account relative to how long they've been with a bank. Someone with many transactions in a short time might be very active, while someone with the same number of transactions over a long period might be lesser. The calculation is quite straightforward. Total transaction divided by number of months they've been a customer. And we also definitely need to handle some potential division by zero issue with if months on book could be zero. Before we create let's create the functions for visualization. I will use like two visualization for here. The for one is like histogram, the other one is box plot. Because we are going to create couple, well, total 3 new engineered features. It would be more efficient if we just use a function for the same task. So I will use a histogram plot and a box plot is both Cbond. And if you're not sure about that, their parameters, then you can take a look at their documents. All right, let's create the first new features. Transaction frequency, I will call it trend freq. Notice we are using NumPy here, and as I said, this is kind of safe to measure. While unlikely in this specific data set, if months on books was 0, dividing by it would cause an error or an infinite values. NumPy lets us handle that case gracefully, assigning 0 if condition is met. So let's take a look at the new features here. I will just briefly take a look at their statistics. Use a describe method. Mean is 1.9 and the median is 1.85 and the minimum is I think it's mean and median is quite close to each other and minimum is 1 point approximately 1.2 and the maximum is like 9.7. So I think the range between the minimum and maximum is quite wide. And let's call the histogram plot function. So as you see the blue curve here, it peaks slightly further to the right than the green curve. This suggests customers who didn't churn tend to have a higher transaction frequency per month on the book. And let's call the box plot. So the median line for the non-churn group is clearly higher than the churn group. So low transaction frequency seems associated with churn, Well, and there's of course overlap, but the difference is quite visible. Let's create the second new features, average transaction value. And the intention is what is the average monetary value for each transaction? Well, this can give us insight into the spending habit of customers. Are they making small and frequent purchase or larger, less frequent ones? The note about handling division by zero is crucial. You will need to decide what to do if a customer has a zero total transaction. Active transaction value, I call it F trend value. Okay, we use a NumPy here. Here is the more crucial. If a customer has a zero transaction, we cannot calculate an average value for transaction. So we'll assign zero in this case, assuming no transaction means zero average value. Dividing by zero directly in pandas might result in a like infinite or non-null value, which could cause issues later. So let's take a look at the basic statistics with a describe method also. So average is 62 and median is 55. I think there is a difference. And minimum is 19 and maximum is 190. So the range of between the minimum and maximum is quite wide also. Let's create the histogram and box plot. Looking at this distribution, like they seems more similar, like either non-churn group and churn groups. Looks like the distribution is the difference of their distribution is kind of negligible. And so let's take a look at the box plot. So the box plot shows the median value for churn group and non-churn group is also quite close. It seems that the pipes customers who churn about the same per transaction on average. This feature might be less differentiating compared to the transaction frequency. So let's move to the last new features. It's called inactive ratio. So the intention here, what proportion of the last year has the customers been inactive? This gives us a clear picture of how inactive a customer has been in the past year as a percentage. Or large or high inactive ratio could be a strong indicator of potential churn. Let's quantify the how inactive a customer has been recently. So we have the months of inactive 12 months column. To make this more relative, let's turn it into a ratio representing the proportion of the last year the customer was inactive. This is an inactive ratio, and I will call it the inactive ratio also. This gives us the value between 0 and 1 and representing the fraction of the last year's the customer shows no activity. Let's take a look at the new features. Oh, so The mean is like a 0.19, a point close to 0.2, and the median is 0.15, like 1.16. So I think it's the median and mean is quite close to, and also minimum is just like a 0, but also maximum is like a 0.5. So I will say is the range isn't so like wide enough here. So let's just take a look at the histogram and box plot too. Okay, so here is the inactive ratio. Wow, look at the histogram. The green distribution is heavily concentrated toward the higher inactive ratio, while the blue is concentrated near low values. And let's take a look at the box plot also. So the box plot makes this even clear. So the median inactive ratio for Churn group, who have been inactive for a large proportion of the last year, are much more likely to churn. This looks very promising feature. So to summarize what we found, inactive ratio shows a strong separation between churn and non-churn groups, highly likely to be a predictive, and trend frequency shows a moderate separation. Low frequency seems linked to the churn, likely useful, and average transaction value shows less and separation or some separation. Its predictive value might be like lower compared to the others. So by visualizing these engineered features against our target, we have gained valuable insight. We have better ideas of which feature might be important drivers of churn, and are more confident moving forward into the feature selection and modeling. So, all right, great. We have calculated our three new features derived from the existing data: transaction frequency, average transaction value, and inactive ratio. These features potentially capture customer behavior nuance that might be useful for our churn prediction model. All right, we have engineered new features and visualized their connection to customer churn. The key next step is feature selection, where it determines which ones should be incorporated into our predictive model. This process involves evaluating the new features, possibly along with the original ones, using specific techniques to find the combination that yields the best predictive power. So we can ask ourselves, why bother selecting features? Why not just throw everything into a model? There are several reasons. Simpler model is easier to understand and explain and maintain. Secondly, reduced overfitting. Less noise and irrelevant information means the model is less likely to fit the training data too perfectly and fail on new data. Improved accuracy. Sometimes removing noise or redundant features actually boost performance. Last but not least, faster training times. Fewer features mean model train quicker. And okay, there are number of ways we can use and apply to choose features which we want to include in the predictive model. And we'll take a look at the examples from two main types. The one of them is filter method. Evaluate features based on their intrinsic properties without involving a specific model. They are fast. Secondly, embedded method. Feature selection is part of the model training process, like tree-based models or regularized in regression. So before we apply the first method, we just need to drop the dummy features first. So here, I only choose numerical features, target feature, and newly engineered features. So the simplest filter method is looking at correlation. We wanted to check two things: predictor versus predictor. High correlation between two predictor features indicated multi-collinearity. They might carry redundant information, and some models don't handle this well. We can visualize this with a heat map later. And secondly, predictor versus target. How strongly is each feature linearly related to churn? We calculated the correlation of each feature with the target column. Higher absolute values suggest a stronger linear break. So let's create correlation metrics first. So it might be hard to find, but just let's take a look at the feature we create, transaction frequency. So this transaction frequency has a highly correlated with the months on book and also total transaction amount and total transaction count. It makes sense because transaction frequency is based on the total transaction amount and total transaction count. And it is more visual or easy to look at if we just take a look at the heat map. So the heat map helps us spot if any predictors are very highly correlated with each other. So look for very bright or dark blue squares of the main diagonal. Remember, the correlation only captures linear relationship. So just like transaction frequencies negatively highly correlated with the months on book and positively highly correlated with the total transaction amount and total transaction count. Let's take a look at the correlation list based on the target. Let's take a look at the first 10 the features highly correlated with the target feature. So total transaction count, transaction frequency, and total transaction change first quarter to last quarter, and total revolving balance and average utilization ratio, and those features highly correlated with the target variable. Let's move to the second method. So tree-based models like random forest naturally evaluate feature importance during training. Features used more open or higher up in the decision trees to split the data effectively get higher importance scores. This is an embedded method. So let's build the simple random forest model with the features we have here. So we built the random forest model simple random forest model here. And let's get the feature importance. Just like a correlation matrix, we see the first 10 highly important features here: total transaction amount, total transaction count, total revolving balance, total transaction change over first quarter to last quarter, and transaction frequency. And those features, existing features and newly engineered features, are highly important in the highly important features. And it would be more easier to see if we just look at the feature importance with bar plot. So as you see, it's quite clear that we see the total number of, there are top 10 features important in the through the embedded method. So just like a total transaction amount and total transaction count and to the credit limit. So the random forest agrees that total transaction amount and total transaction count are very important. Interestingly, total revolving balance and total transition count change first quarter to last quarter also rank high. Our engineered average transaction balance is quite prominent here too. So the plot helps visualize the relative importance here, and just like above the feature importance figure. So we have results from these two different methods. So what now? So look for the consistency based on first method and second method. Which features appear highly ranked across multiple methods? So total transaction count, total transaction amount, total revolving balance, and average utilization ratio, and other newly engineered features. Secondly, consider multi-collinearity. So as I say, the transaction frequency is based on total transaction amount and total transaction count. So if the heat map shows very high correlation between those high-ranked features, we might choose just one of them. And thirdly, user domain knowledge. Does a feature make a business sense as a churn predictor? And last but not least is the experiment. The ultimate test is often building models with a different feature subset and evaluating their performance using cross-validation. So based on this analysis, a good starting set for our model might include the consistently top-ranked original features plus potentially transaction frequency, average transaction balance, and inactive ratio, especially inactive ratio, which looked very distinct visually. Feature selection is a blend of automated techniques and informed judgment. It's a key step toward building robust and interpretable models. Next, we'll finally take our selected features and train some classification models.